Good morning, afternoon, everyone. My name is Potsatorn Thongthainun, and together with my teammate Ketsuda Chantabut, we are excited to present our project for the Control Engineering course. Our topic today is the control design of a mass spring damper system. The mass spring damper, or MSD system, is a fundamental model in mechanical and control engineering. It represents everything from car suspensions to seismic protection in skyscrapers. Today, we will walk you through the mathematical modeling, our control strategies, and the final simulation results. Let's begin with the physical foundations of our project. To design an effective controller, we must first understand the dynamics of the system we are working with. Our system is a classic mass spring damper model, which consists of three fundamental physical components. First, the mass, m, which represents the inertia of the system. Second, the spring, k, which provides a restoring force proportional to the displacement. And third, the damper, which dissipates energy and provides a resistive force proportional to the velocity. By applying Newton's second law, specifically the principle that the sum of forces equals mass times acceleration, F equals ma. However, analyzing differential equations in the time domain can be complex for control design. To simplify this, we applied the Laplace transform to transition our model into the frequency domain. This allowed us to derive the transfer function, g of s equals 1 over ms squared plus cs plus k. For this specific simulation, we defined our parameters as m equals 1, c equals 0.5, and k equals 2. Based on these values, we calculated the damping ratio zeta, which confirmed that our configuration results in an underdamped system. In practical terms, this means the system will naturally overshoot and oscillate before eventually reaching equilibrium. Before implementing a controller, we must analyze the open-loop performance to identify the problems we need to fix. When we look at the open-loop step response of our system, the performance is quite poor. The system exhibits a very high overshoot, nearly 57%, and it takes a significantly long time to settle at the desired position. In the context of precision engineering or robotics, such high oscillation is unacceptable because it could lead to system wear or even instability. This brought us to the core of our project, the feedback controller design. We evaluated three different control strategies to find the best solution. Proportional, P control. This was our starting point. Increasing the proportional gain makes the system respond faster, but it has a major drawback. It cannot eliminate the steady-state error. The system gets close to the target, but never quite reaches it. Proportional integral. In the integral, we added the integral term to solve the error problem. While the PI controller successfully drives the steady-state error to zero, it often introduces more sluggishness and can actually increase the overshoot if not tuned perfectly. PID control. Finally, we implemented the full PID controller by adding the derivative D term. We introduced what we call predictive braking. The D term anticipates the error's trend and applies a counterforce to dampen the oscillations before they get too high. Moving on to the implementation phase, we used MATLAB and Simulink to test our design. The simulation results were highly successful. By using the PID Tuner app and manual refinement, we achieved a response that is both fast and stable. With our final tuned PID parameters, we successfully reduced the settling time from over 10 seconds down to just 3.2 seconds. More importantly, we suppressed the overshoot from 57% down to a very manageable 12%. This meets all the standard performance specifications for a robust control system. Beyond just looking at the time response curves, we also conducted a frequency domain analysis to ensure stability. We generated a Bode plot to calculate the system's safety margins. Our design achieved a phase margin of 62 degrees. In control theory, a phase margin between 45 degrees and 60 degrees is considered ideal for a stable and robust system. This 62-degree margin indicates that our system will remain stable even if there are slight changes in the physical mass or unexpected friction in the real-world environment. To conclude our presentation, we have successfully walked through the entire control engineering workflow, from deriving mathematical models using physics to analyzing system limitations, and finally, designing a PID controller that optimizes performance. We have demonstrated that while the mass spring damper system is inherently oscillatory and difficult to manage in its natural state, the application of a well-tuned PID controller provides the perfect balance between speed, accuracy, and stability. This project reinforces the importance of the derivative and integral terms in achieving precision in mechanical systems. That concludes our presentation for the final project. We would like to thank you for your attention. We are now open to any questions, comments, or feedback you may have. Thank you. Now we move into the practical implementation part. We build our Simulink model using the script MSD, Simulink Setup.m, which automatically constructs the entire block diagram programmatically, no manual drag and drop required. The signal flow has 5 main blocks. Step input sends our reference of 1 meter. Then the sum block computes the error between the reference and the current output. That error feeds into the PID controller block, which calculates the control signal UT. The control signal then drives the transfer function block, which represents our MSD plant GS. Finally, the scope block records the output displacement XT. The negative feedback loop connects the plant output back to the sum block, continuously correcting the error in real time. For the solver, we used OD45, a variable step, Ranjkuta fourth, fifth-order method, which is well suited for smooth continuous systems like ours, with a relative tolerance of 1 × 10 to the power of -6. Finding the right values for Kp, K, and Kd was done systematically in 6 steps. We started with the MATLAB Pit Tuner app to get a reasonable initial set of parameters based on our target bandwidth. Then we computed the closed-loop transfer function using feedback and checked that all poles are in the left half plane, confirming stability. Next, we ran the step simulation and extracted performance metrics using step info. From there, we manually refined the parameters one at a time. And the key rule is, Kp up means faster response but more overshoot. Kd up means less overshoot. Key up means faster elimination of steady-state error. Finally, we verified the stability margins using the margin command, making sure GM exceeded 6 decibels and PM exceeded 45 degrees before accepting the final design. This graph was generated by MSD control main.m and shows the step response of all 3 controllers on the same plant. The blue line P controller responds quickly at first, but overshoots by about 35% and never quite reaches the 1 meter target. The output settles around 0.71 meters, leaving a permanent steady-state error of approximately 0.29 meters. The green line PI controller does reach the 1 meter reference and eliminates the steady state error. However, it takes longer to settle, and you can see the response oscillates more before stabilizing. The purple line PID controller performs best across the board. It reaches the set point quickly, the overshoot is small at around 12%, and it settles the fastest of the three. The red dotted band marks the plus or minus 2% settling zone around 1 meter. We use that to measure settling time precisely. This bode plot was generated directly from the command margin C, PID times G, in our main script. The top graph shows magnitude in dB versus frequency. The point where the magnitude crosses 0 decibels is called the gain crossover frequency. This is where we measure phase margin. The bottom graph shows phase in degrees. At the gain crossover frequency, the phase is still 62 degrees away from 180 degrees. That 62 degrees is our phase margin. The gain margin of 18 decibels means the open loop gain would need to increase by a factor of nearly 8 before the system becomes unstable. That is a very comfortable safety buffer, and it tells us our PID design is not only stable, but also robust to plant variations and modeling uncertainty.
To wrap up our presentation, let's focus on the key insights from our study. We began by modeling a mass spring damper system, which serves as a fundamental example of a second-order mechanical system. With our parameters of mass equals 1, damping equals 0.5, and spring constant equals 2, we identified the system as being underdamped with a natural frequency of 1.414 radians per second and a damping ratio of 0.177. This low damping ratio is exactly why the system is so prone to oscillation, making it a perfect candidate for advanced control design. Key core of our project was finding the right balance between speed and precision, looking at our performance comparison. First, our proportional P controller proved that increasing gain can speed up the response, but it could not eliminate the steady state error of 0.29 meters because our plant is a type 0 system. Next, the PI controller successfully removed the error through its integral action, but it made the system significantly slower with a settling time of 5.5 seconds. Ultimately, the PID controller was the clear winner. By using our tuned values of Kp equals 4.5, K equals 2, and Kd equals 0.8, we achieved a settling time of only 3.2 seconds and an overshoot of just 12%. This demonstrates that the PID structure provides the most comprehensive control for this type of mechanical load. Beyond just looking at the graphs, we had to ensure the system is safe and robust for real-world use. Our stability analysis using the bode plot confirmed that the PID system has a gain margin of 18 decibels and a phase margin of 62 degrees. These margins are well above the standard requirements of 6 decibels and 45 degrees. What this means in practice is that our design is robustly stable. It can handle small changes in mass or unexpected friction without becoming unstable or losing performance. Finally, we must consider practical constraints. In a real laboratory or industrial setting, the derivative term can sometimes amplify high-frequency sensor noise. Therefore, our professional recommendation is to use a derivative filter in actual hardware implementation to ensure a smooth control signal In conclusion, this project has successfully bridged the gap between mathematical theory and practical software simulation. We have shown that with proper tuning, a PID controller can transform an unstable, oscillating system into a precise and reliable one. Thank you very much for your time, and we are now ready for any questions.